In this video, we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data. In linear regression, we have a training set like that shown here. Remember our notation, m was the number of training examples, so maybe m equals 47. And the form of our hypothesis, which we use to make predictions, is this linear function. To introduce a little bit more terminology, these theta 0 and theta 1, right, these theta i's are what are called the parameters of the model. And what we're going to do in this video is talk about how to go about choosing these two parameter values, theta 0 and theta 1. With different choices of the parameters theta 0 and theta 1, we get different hypotheses, different hypothesis functions. I know some of you will probably be already familiar with what I'm going to do on this slide, but just to review, here are a few examples. If theta 0 is 1.5 and theta 1 is 0, then the hypothesis function will look like this. Right? Because your hypothesis function will be h of x equals 1.5 plus 0 times x, which is this constant value function that's just flat at 1.5. If theta 0 equals 0, theta 1 equals 0.5, then the hypothesis will look like this. And it should pass through this point 2, 1, since you now have h of x, or really h substrate theta of x, but sometimes I'll just omit theta for brevity. So h of x will be equal to just 0.5 times x, which looks like that. And finally, if theta 0 equals 1 and theta 1 equals 0.5, then we end up with a hypothesis that looks like this. Let's see, it should pass through the 2 point like so, and this is my new h of x, or my new h subscript theta of x. All right, well, you remember I said that this is h subscript theta of x, but as a shorthand, sometimes I'll just write this as h of x. In linear regression, we have a training set, like maybe the one I've plotted here. What we want to do is come up with values for the parameters theta 0 and theta 1, so that the straight line we get out of this corresponds to a straight line that somehow fits the data well, like maybe that line out there. So how do we come up with values theta 0, theta 1 that corresponds to a good fit to the data? The idea is we're going to choose our parameters theta 0, theta 1 so that h of x, meaning the value we predict on inputs x, that this is at least close to the values y for the examples in our training set, for our training examples. So in our training set, we're given a number of examples where we know x, the size of the house, and we know the actual price it was sold for. So let's try to choose values for the parameters so that at least in the training set, given the x's in the training set, we make reasonably accurate predictions for the y values. Let's formalize this. So in linear regression, what we're going to do is I'm going to want to solve a minimization problem. So I'm going to write minimize over theta 0, theta 1. And I want this to be small, right? I want the difference between h of x and y to be small. And one thing I might do is try to minimize the squared difference between the output of my hypothesis and the actual price of a house. Okay? So let's fill in some details. You remember that I was using the notation xi comma yi to represent the ith training example. So what I want really is to sum over my training set, sum from I equals 1 to m, of the squared difference between, this is the prediction of my hypothesis when it is input the size of house number I, right, minus the actual price that house number I was sold for. And I want to minimize a sum over my training set, sum from I equals 1 through m, of the difference, of the squared error, squared difference between the predicted price of a house and the price that it was actually sold for. And just to remind you of your notation, m here was the size of my training set, right? So the m there is my number of training examples, right? That hash sign is the abbreviation for number of training examples. Okay. And to make some of our later math a little bit easier, I'm going to actually look at 1 over m times that. So we're going to try to minimize my average error, which is going to minimize 1 over 2m. Putting the 2, the constant 1/2 in front, it just makes some of the math a little bit easier. So minimizing 1/2 of something, right, should give you the same values for the parameters theta 0 and theta 1 as minimizing that function. And just to make sure this equation is clear, right? This expression in here, h subscript theta of x, this is our usual, right? That's equal to this plus theta 1 xi. And this notation, minimize over theta 0 and theta 1, this means find me the values of theta 0 and theta 1 that causes this expression to be minimized. And this expression depends on theta 0 and theta 1. Okay? So just to recap, we're posing this problem as find me the values of theta 0 and theta 1 so that the average, or really 1 over 2m times the sum of squared errors between my predictions on the training set minus the actual values of the pulses on the training set is minimized. So this is going to be my overall objective function for linear regression. And just to rewrite this out a little bit more cleanly, what I'm going to do is, by convention, we usually define a cost function, which is going to be exactly this, that formula that I have up here. And what I want to do is minimize over theta 0 and theta 1 my function j of theta 0 comma theta 1, where, just to write this out, this is my cost function. So this cost function is also called the squared error function, or sometimes called the squared error cost function. And it turns out that why do we take the squares of the errors? It turns out that the squared error cost function is a reasonable choice and will work well for most problems, for most regression problems. There are other cost functions that will work pretty well, but the squared error cost function is probably the most commonly used one for regression problems. Later in this class we'll talk about alternative cost functions as well, but this choice that we just had should be a pretty reasonable thing to try for most linear regression problems. Okay, so that's the cost function. So far we've just seen a mathematical definition of this cost function, and in case this function j of theta 0, theta 1, in case this function seems a little bit abstract and you still don't have a good sense of what it's doing, in the next video, in the next couple of videos, I'm actually going to go a little bit deeper into what the cost function j is doing and try to give you better intuition about what it's computing and why we want to use it.